Hello. In today's lesson, we will discuss a new concept, and that is electric potential. What does potential means? Well, if I raise an object, it has potential energy. Why? Because it has the ability to do work. Potential is actually the ability to do work. What is electric potential? It is useful to compare electric potential to gravitational potential. So let's compare gravitational and electric fields. When you have a gravitational field, you have a gravitational potential. Similarly, an electric field will then define an electric potential. You are familiar with gravitational potential energy. Now, if I want to raise an object through a height h, then the force I apply will do external work. Now, when I use the force and that force moves in the upward direction, the gravity also is applying a force. See, if the force I apply is upward, the force the gravity applies will be downward. Therefore, if the work I do is positive, the work gravity does will be negative. So an external force does work against gravity to raise the object, to raise the potential energy. The work done by gravity on the object will be negative. I hope you understand that concept, because the object is moved up. The applied force is also upward. The direction of the force and the direction of displacement are the same for the external force. That means that work is positive. But the direction of the force of gravity is downward. And when you move the object upward, the work done by gravity is negative. So, the negative work done by gravity raises the potential energy. Now that concept is very important. So gravity does negative work. Now, when you allow the object to fall, the displacement and the direction of the gravitational force are both the same. That means when the object falls, gravity does positive work. Therefore, tell me, what is the total work done by gravity in raising the object and then bringing it back to its original position? While raising the object, the work done by gravity is negative. While the object falls back, the work done by gravity is positive. So what is the total work done when the object is raised through that closed path? You see, when I raise the basketball, the work done by gravity is negative. When I drop the basketball, the work done by gravity is positive. The total work done by gravity in that closed path is zero. Now, what do you call such a field? We talked about it in Physics 1. You see, a field where the total work done in a closed path is zero is called a conservative force field. Now, this work done by the external force gives the object a potential energy U. So the work done by the external force raises the potential energy, which is the same as saying that the negative work done by gravity raises the potential energy. The potential energy, therefore, is a measure of the negative work done by gravity. I hope that concept is clear. It's very important to know that. When the object is allowed to fall, the gravity does positive work. So positive work by gravity lowers the potential energy. and the negative work done by gravity increases the potential energy of the object. The net work done on the object by the force of gravity in the closed path is zero. A force field where the net work done in a closed path is zero is called a conservative force field. Gravitational field is a conservative force field. In the same way, electric field is a conservative force field. You see, the motion of an electric charge in an electric field is the same as the motion of an object in a gravitational field. Potential energy in a conservative field is the negative of the work done by the conservative force. In a gravitational field, the conservative force is the gravitational force. In an electric field, the conservative field is the electric field. Now, how do I write this in a mathematical notation? We say U stands for the potential energy. The potential energy is negative of the work done by the conservative force. F dot ds is the small amount of work done by this force when the displacement is ds. And integrating that work through the entire displacement will be a measure of the potential energy. Now, like gravitational field, electric field is a conservative field. Here we study the motion of electric charges in an electric field, just like we study the motion of objects in gravitational field. In electric field, we study the motion of electric charges. But there is a small problem with the electric field. There are two types of electric charges. So which one do we choose as our test charge? Well, we have settled on it long ago. What is our test charge? Our test charge is a positive charge. We have chosen a positive charge as a test charge. Therefore, we will now be talking about the motion of positive charge in an electric field. Now, a positive test charge is placed in the electric field produced by this positive charge. Now remember, the electric field due to a positive charge will be diverging from the charge. The field lines will be originating from it. So a positive test charge is placed in a field produced by a positive charge. An external force has to do work to move the test charge from A to B. You see, because the field is directed away from the positive charge, if you want to move a positive test charge towards the positive charge, an external force needs to do work. In the same way, when you want to raise an object in the gravitational field, an external force has to do work. So, moving a test charge towards a positive charge is like raising an object in the gravitational field. An external force has to do work to move this positive test charge from A to B. Now tell me, when the object is moved from A to B, is its potential increasing or decreasing? When the positive test charge is moved from A to B, its potential increases. So the electric field does the negative work on the test charge, increasing its potential energy. So when the external force moves the object from A to B, you can see the external force is directed from A to B. If that work done is positive, then the work done by electric field will be negative, because the electric field is directed from B to A. So In order to increase the potential energy, we move the test charge from A to B. And when you do that, the electric field does negative work on it. Therefore, how do we measure or how do we define electric potential? The electric field does negative work on the test charge, increasing its potential. That means the negative work done by the conservative electric field is a measure of the increase in potential of the test charge. When the test charge is allowed to move, if you now leave that test charge will fall back to A. Just like the basketball falls back to a lower potential. When you allow the test charge, after placing it at B, if you allow it to move, it will move back to A and it will move away. What is the direction of motion of a positive charge in an electric field? You can see, if you leave the positive charge, it will move away from this positive charge in the direction of the electric field. Now, when it does that, its potential decreases. Therefore, we can very conveniently say that the direction of an electric field is the direction of decreasing potential. When the test charge is allowed to move, it falls to a low potential in the direction of the electric field. That means when the electric field does positive work. When the electric field does positive work, it decreases the potential of the test charge. Therefore, the potential decreases in the direction of the field, a very important concept. The direction of an electric field is the direction of decreasing potential. The electric field is directed from B to A. B corresponds to a high potential and A corresponds to a low potential. The direction of the electric field is the direction of decreasing potential. The potential energy of a test charge at infinity will be zero. If you leave the test charge, it will go all the way to infinity where its potential energy will be zero. So we will assume that the potential energy is maximum near the positive charge. And as you go away, the potential decreases. When the test charge is moved opposite to the direction of the field, the gain in potential energy is a measure of the negative work done by the electric field. I am repeating this concept because it is very important. When you move the test charge opposite to the electric field, the gain in potential energy is a measure of the negative work done by the electric field. Electric field is a conservative force field. And we write it like this one more time. The gain in potential energy U is the negative of the work done by this conservative force field, which is the electric field now. The same statement we made for the gravitational field. Now consider an electric field E generated by a positive charge. Here is the positive charge, and you have the electric field generated by this positive charge. So that's the electric field. Since E varies with the distance from the charge, the electric field has different values at different points. If you now move from a point close to the positive charge and away from it, you can see the electric field will decrease. The field lines actually tell you that story. How? A region where the field lines are closer, the strength of the field is greater. As you move away, the field lines are widely separated, the strength of the field decreases. So as you move away from the positive charge, the strength of the electric field decreases. Alright, let's place a test charge Q0 in here. A test charge Q0, I want this Q0 to be there. So the Q0 is actually, this is my Q0. Alright? So a test charge Q0 placed in the electric field will experience a force. What is the force experienced by a charge placed in the electric field? Now remember, the definition, the basic definition of electric field is the force per unit charge. So if E is the force per unit charge, if you place a charge Q0 in that field, that the force experienced by that Q0 will be F equal to E times Q0. So a test charge placed here will experience a force E times Q0. Alright, let me take that away now. Now the force F equal to E times Q0. You can see that arrow is supposed to be here and somehow it got displaced. This is the arrow that I meant to put there. That's the arrow representing the force. That force F equal to E times Q0. Alright. Now to move the test charge in the direction of increasing potential. What is the direction of increasing potential? Towards the positive charge. An external force needs to do work. That means an external opposite force is needed and the work done will be equal to negative E Q0. So if you want to move this test charge in the direction of increasing potential, an external force needs to be applied in the opposite direction, and that force will be therefore negative EQ0, because if the force directed in the direction of the field is E times Q0, that is the force experienced by this charge. If you now want to move this charge in the opposite direction, in the direction of increasing potential, you need to apply this opposite force on it. Now, when the test charge is moved at distance dr, if this is the distance dr, if you move the test charge at distance dr, this force is moving through a distance dr. What is the increase in potential energy? The increase in potential energy is a measure of the work done. And the work done is this force multiplied by this displacement. And the force is negative EQ0. So the work done to move this test charge Q0 through a distance dr will be F times dr. That will be, this is F, negative EQ0 is the F times dr. And that is a measure of the increase in potential energy. Now therefore, what is the increase in potential energy per unit charge? This is the increase in potential energy of a charge Q0. What is the increase in potential energy per unit charge? That will be du over Q0. And that will be negative EdR. Now this has some significance. du over Q0 is called the increase in potential per unit charge, and that is equal to negative EdR. Now this is a measure of the potential difference between the 2 points. the potential difference between the 2 points, between this point and this point. You see, when you move the object from the initial position to the final position, its increase in potential energy per unit charge is negative EdR, and this is a measure of the potential difference between the 2 points. So what is the definition of potential difference between 2 points in an electric field? Potential difference between 2 points in an electric field is the increase or decrease, change in potential energy per unit charge. And it is a measure of the work done on a unit test charge to move it through a distance dr. So the potential difference between 2 points is a measure of the work done to move a unit test charge from one point to the other. You must understand that definition very well. Potential difference between 2 points in an electric field is a measure of the work done in moving a unit test charge from one point to the other. Now, it is similar to the potential difference between 2 points in the gravitational field. Potential difference is the measure of the work done in moving a unit mass from one point to the other. In the same way, in an electric field, potential energy is a measure of the work done, or potential difference between 2 points is a measure of the work done in moving a unit test charge from one point to the other. So we have du over q0 equal to negative EdR. What does du over q0 define? Is the potential energy per unit charge, and this is a measure of the potential difference between 2 points at a distance dr apart. We will use V to represent potential at a point, and delta V the potential difference between 2 points separated by a small distance delta r. Then du by q0 will be your V, because that will be a measure of the potential. So therefore we have delta V, the potential difference. Delta V is the potential difference. du over q0 is a measure of the potential difference between 2 points separated by distance dr. If delta V is the potential difference between 2 points separated by a distance dr, then delta V equal to negative E delta R. Or E, electric field, can now be defined in terms of the potential difference. A very important concept again. E, the electric field, is negative of delta V divided by delta R. What does delta V divided by delta R define? It is the rate at which the potential changes with distance. You see that? In other words, we can actually write this using calculus. Alright, that's equal to negative dV over dr. So electric field is negative of the rate of change of potential with respect to distance. That is a very important equation. E equal to negative dV over dr. Well, if you now consider the electric field in the x, y and z direction, we can use this equation. This is the general equation for any direction. Electric field in any direction is negative of dV over dr. That means I can rewrite this. If I use E sub x, electric field in the x direction will be negative of dV by dx. Electric field in the y direction will be negative of dV by dy. Electric field in the z direction will be negative dV by dz, and so on. Now notice that the potential V decreases in the direction of the direction of the electric field. You can see the E and V are oppositely directed. That means the direction of the electric field is the direction of decreasing potential. We talked about it earlier. E equal to negative dV by dr. Alright, suppose V, the potential, is a function of x, y, z, defines the electric potential in a three-dimensional space. If you consider, see, electric field is a three-dimensional space. So if you take any point in the electric field, the potential at that point will be a function of x, y, and z. Then the partial derivative of this potential function with respect to x will represent the electric field intensity in the x direction. Now that is the meaning of E equal to dV by dr. You see, if we have an electric field in a region and you take a point R at a distance x from the origin, at a distance r from the origin, the electric field at this point is negative dV by dr. And you can express it using x components, y components, and z components. In other words, Ex is negative. Now, you see, some of you have some idea about what this is, but most of you don't understand this. Now, there is a difference between, let me show you that. There is a difference between dV by dx and del V by del x. You see, dV by dx is the straight derivative of V with respect to x. Suppose V is a function of x, y, and z. You see, potential at a point in an electric field is a function of x, y, and z. You read this quantity as del V by del x. And what does this quantity represent? This represents the rate of change of potential with respect to x when y and z are considered to be constant. It is called the partial derivative of v with respect to x. In the same way, the partial derivative of v with respect to y will be del v by del y. So I can have partial derivative del v by del y and del v by del z. So del v by del x is the derivative of v with respect to x when y and z are constant. Del v by del y is the derivative of the potential function v when x and z are constant. Del v by del z is the derivative of the potential function with respect to z when x and y are constants. So I can write alright. So I can now write Ex equal to negative del V by del x, Ey equal to negative del V by del y, and Ez equal to negative del V by del z. So the electric field in the x direction is negative of the derivative of the potential function in the x direction. The electric field in the y direction is negative of the derivative of the potential function in the y direction, and the electric field in the z direction is negative of the derivative of the potential function in the z direction. They are called the partial derivatives in the x, y, and z direction. We can combine all this and write a single equation for the potential function. This is the same as saying that the electric field in a region is the negative of the gradient of the potential function. Negative of the gradient. What's the meaning of gradient? Well, derivative is the gradient. So, the electric field is a measure of negative of the gradient of the potential function. Now, in calculus, we can combine all these three and write an expression for the gradient. The gradient of a function in space is represented by the operator. Now look at that operator. We call that del. The operator del. And say del v. In other words, you use that operation on that v. Now what is that operation? That operation consists of finding the derivative of this with respect to x in the x direction, that is I. Then find the derivative of this in the y direction, that is j. And then find the derivative of that in the z direction, that is k. So del v equal to del v by del xi plus del v by del yj plus del v by del zk, and this represents a potential function in a three-dimensional electric field. Electric field in a three-dimensional space is given by E equal to negative, you can see, I don't think you can see my right hand side, E equal to negative dv over dr. Now this is the same thing. E equal to negative del v, negative of the gradient of the potential function. Electric field is a measure of the negative of the gradient of the potential function. Now let's do an example. Find the electric potential at a point 2, negative 3, 5 in space, where the electric potential is given by Vxyz equal to x squared plus y squared plus z squared. Well, Vx potential is a function of x, y, and z. Now, if Vxyz equal to x squared plus y squared plus z squared, what is del v by del x? That's very simple for you. Find the derivative of v with respect to x when y and z are constants. That is what we call the partial derivative of v with respect to x. When y and z are constants, the derivative of y squared and z squared will be 0. So del v by del x is 2x. Alright, what is del v by del y? Will be 2y. When you want to take the derivative of v with respect to y, x and z will be constant. So del v by del y equal to 2. What is del v by del z? That will be 2z. And therefore, what is gradient of the potential function? Gradient of the potential function is del v by del xi plus del v by del yj plus del v by del zk. The gradient of the potential function has the x part, y part, and the z part. Well, that will be del v by del x is 2x, del v by del y is 2y, and del v by del z is 2z. That will be 2xi plus 2yj plus 2zk. And what is the value of this at this point, 2, negative 3, 5? Well, you got electric field E equal to negative del V. I want to make a small correction in the problem. The problem must read like this: find the electric field at a point, not the electric potential. I gave you the potential function. I want you to find the electric field. So make that correction. Find the electric field at a point 2, negative 3, 5, where the potential function is given. Now, E, the electric field, is negative del V. It is the same equation that we used, E equal to negative dV over dr. And negative del V is negative 2xi plus 2yj plus 2zk. And let's now find the value of that at the given point. Now the value of the electric field at the point 2, negative 3, 5, replace x by 2, y by negative 3, and z by 5, and that will give you negative of 2 times 2i plus 2 times negative 3j plus 2 times 5k, and that is negative 4i minus 6j plus 10k. In other words, what it tells you is, at this point, the electric field will be in such arbitrary direction so that its x component will be negative 4, y component will be negative 6, and z component will be 10 Newton per Coulomb. Now, potential at a point in an electric field, we know delta V equal to negative E dr. That's what we obtained some time ago. Now consider 2 points A and B in the electric field produced by this charge Q. Now, that's the charge Q. This is point A and this is point B. The electric field at a point distance r from a charge Q. Alright, you can tell me that. What is the electric field at a point distance r from a charge Q? Will be kq over r squared. E equal to kq over r squared. Now that means delta V equal to, if you now apply that for point A, delta V equal to negative E, I'm going to replace E by kq by r squared times dr. Now A is at a distance r1 from the center of the charge. If this distance is r1 and B is at a distance r2 from the charge. Now what does delta V represent? Delta V represents the potential difference between the points A and B. The potential difference between the points A and B is negative E dr, where we assume that dr is so small that E will remain a constant. You see, in other words, A and B are very close together. The distance dr is so small that we will assume that the field in that region dr will remain a constant kq over r squared. The potential difference between A and B can now be obtained by integrating delta V. If you integrate now this delta V from r equal to r1 to r equal to r2, then we can obtain a measure of the potential difference between A and B. So VR2 minus VR1, what does that tell you? VR2 is the potential at a point distance R2 from the charge. VR1 is the potential at a point distance R1 from the charge. VR2 minus VR1 is a measure of the potential difference between the 2 points A and B, equal to integral R1 to R2 negative EdR, negative KQ over R squared dr. Alright, now K is a constant, is that right? And Q is a constant, we can take them out. So that will be KQ times integral, well, let me write that step for you. That will be equal to KQ times integral R1 to R2 negative 1 over R squared dr. Now, what is integral of negative 1 over R squared dr? Any elementary calculus student should know that. You know, what is the derivative of 1 over x with respect to x? You know that? The derivative of 1 over x with respect to x is negative 1 over x squared. Therefore, if you integrate negative 1 over x squared with respect to x, you should get 1 over x. In the same way, integral of negative 1 over r squared dr is 1 over r. So, this will be equal to KQ times 1 over r, and the lower limit is r1, the upper limit is r2. And what I have done in this step is write this with the KQ inside. So, integral r1 to r2 negative KQ over r squared dr equal to KQ over r from r1 to r2. Now we will replace this r by r2 for the upper limit minus replace r by r1 for the lower limit. So that will be KQ over r2 minus KQ over r1. And that is potential at a distance r2 minus potential at a distance r1. Now, suppose we choose R2 to be at infinite distance from the charge we have. Then, if you say R2 is infinite, and we say suppose the potential at infinity is 0, that means VR2 we are going to call 0. When that R2 is infinite distance from the charge, this VR2 will be 0. And also one more quantity on the right side will become 0. When R2 is infinity, KQ over R2, anything divided by infinity is 0. So look at the change we can make there. 0 minus VR1, negative VR1 equal to, when R2 is infinity, this quantity is 0. 0 minus KQ over R1 is negative KQ over R1. And what does that give you? If you now replace R1 by R, instead of calling the distance R1, we're going to say let the distance of the point be R, measured from where? Measured from the center of the charge. If you now replace this R1 by R and cancel the negative signs from both sides, we get VR, potential at a distance R from a charge Q, is KQ over R. Now look at that beautiful and very interesting, very, very important equation. The electric potential at a distance R from a charge Q is V equal to KQ over R. So take a note, make a note of that and keep it with you. Now this is a measure of the potential at a distance R from a charge Q. Now, one thing we must understand, if the potential due to a positive charge is a high potential, then the potential due to a negative charge will be a low potential. You see that? remember the direction of motion of a positive charge. If you place a positive charge in this field, the direction of motion of the positive charge will be the direction of the electric field, which is the direction of decreasing potential. So the potential near a positively charged object is a high potential. The potential near a negatively charged object is a low potential. So a test charge, when placed in the electric field, will flow. Is it reasonable for me to say it flow? It will flow from a high potential to a low potential in the direction of decreasing potential, in the direction of the electric field. All those concepts are the same. Consider the electric field between a positive charge and a negative charge. The potential at a distance r from the positive charge will be positive kq over r. The potential at this point due to this positive charge q will be positive kq over r. There you are. And if you now consider a point, now what is the potential at that point due to the negative charge? If you take a point here at a distance r from the negative charge, the potential due to the negative charge will be negative. You need to indicate that. So potential at this point due to the negative charge will be negative kq over r. The potential due to a positive charge will be positive, high potential. Potential due to a negative charge will be a negative potential. Well, does it mean that the potential is a vector quantity? No, potential is a scalar quantity. While electric field is a vector quantity, potential is a scalar quantity. Potential at a point in an electric field is a measure of the work done in moving a unit test charge from infinity to that point. Now, you remember earlier on we defined the potential difference between 2 points is a measure of the work done in moving a unit test charge from one point to the other. And when one point is infinity, you can define the potential at this point as a measure of the work done in moving a unit test charge from infinity to that point. Now that is the physical meaning of potential at a point. Potential at a point in an electric field is a measure of the work done in moving a unit test charge from infinity to that point. It is the same as saying in a gravitational field, gravitational potential at this point is a measure of the work done per unit mass in lifting it through height h. In a similar way, the electric potential at a point is a measure of the work done in moving a unit test charge from infinity to that point. Since potential is the work done per unit charge, what is the unit for measuring potential? It is measured in joules per coulomb. Alright, I will be asking you this concept every now and then as we go on. Electric potential is a measure of the work done per unit charge. It is measured in joules per coulomb and it is called the volt. So what is the unit for measuring electric potential? Electric potential is measured in a unit called volt. And what is 1 volt equal to? 1 volt is 1 joule per coulomb. Suppose I say the electric potential at this point is 5 volt. What is the meaning? It means in order to move a unit test charge from infinity to this point, the work that needs to be done is 5 joules. 5 joules per coulomb. What is the meaning that the potential difference between 2 points is 5 volt? It means to move a unit test charge from one point to the other, you need to do an amount of work 5 joules per coulomb. Alright? So keep these ideas alive in your mind. Volt is joules per coulomb. Now look at the electric field. We can now obtain a unit for electric field from this. Well, potential difference is measured as joules per coulomb, and electric field is delta V divided by delta R. So give me another unit for electric field. Well, when I ask you another unit, do you know one unit that we measure electric field already? Yes, electric field is a measure of, alright, it is Newton per coulomb, work done, the force per unit charge. Electric field is measured as the force per unit charge, Newton per coulomb. You can also measure electric field in delta V divided by delta R. Delta V, the potential difference, is measured in volt, and delta R, the distance, is measured in meter. Therefore, volt per meter is another unit of electric field. Alright, if I give you a 1 point extra credit, I want to see how many of you will want to attempt that. Is Newton per coulomb the same as volt per meter? Now, if anybody can show that these two are the same by writing the necessary steps, I will give you 1 extra credit point. Newton per coulomb is actually the same as volt per meter. Now, write down the steps and show me how these are the same. I will give you 1 extra credit point. Well, I'm going to stop this one here. I will do a second part of this lesson later on.